I'll simply say I thanked Willie May and John Morgenthau for inviting me to provide this seminar this afternoon. I was here 4 years ago, and I visited also many of the researchers and the faculty involved in the engineering school. And it's always a pleasure to come back to Morgan State. I will talk to you about our World Trade Center investigation, which planning for which actually pretty much started at the end of the week of 9/11 of 2001. I think just for all of us, wherever we were, that event was quite etched in our minds, has been etched in our minds, and was horrendous to see two very, very tall buildings, 110-story buildings that collapsed, along with a number of the other buildings surrounding the towers that collapsed and killed. At that time, we did not know how many people lost their lives, but we thought there were many more that may have lost their lives. At the end, we found close to 2,750 lives were lost. It was one of the worst ever building disasters in recorded history. And of course, these were the outcome of the terrorist attacks by a bunch of people who flew planes into buildings in New York and in the Pentagon, and tried to do the same thing to another building, presumably in the Capitol. As well. So what made it, in addition to the loss of life, that 2,749, was the fact that 400 of those people who were lost on that day were emergency responders. They were firefighters, police officers, security folks, and others. That by itself is the largest loss of life for this group in a single incident. Right after 9/11, there were expressions of concern from the families of the victims, the surviving occupants, and others to have a full accountability of what happened on 9/11. Why did their loved ones die? And that interest on the part of the public, along with the interest on the part of Congress, the congressional delegation, particularly from New York, as well as the private sector, led to the demand for a comprehensive response to this World Trade Center disaster, besides the immediate response, recovery on site, was the need for a investigation as to why and how these buildings collapsed, because ultimately, even though the terrorists flew planes into these buildings, many of the loved ones died when the buildings actually collapsed. Congress held 2 hearings in 2002 in the spring and passed the National Construction Safety Team Act. And the president signed it into law on October 1 of 2002. Our investigation formally started in August of 2002. So we spent the first 9 or 10 months planning for the investigation. We went up to New York. We participated in teams that went there to look at, as you will see here, to look, and in the pictures, you see one of our staff members at the salvage yards in New York, looking at the pieces of steel that we ultimately were able to bring 236 pieces of those steel, the only physical evidence available for us to do our analysis. We had an extensive collection of photographic and communication data, unprecedented, because this was the era of the smartphone. And people had taken a lot of photographs, a lot of videos. And so we were able to access that. We also got access to all of the design, construction, maintenance, and inspection documents for these buildings since the middle or early 60s, when these buildings were originally conceived and designed, all the way up to a few years before the collapse. We ultimately ended up studying 3 buildings. From the scoping, what we wanted to do, we wanted to look at 2 buildings that where the loss of life was directly involved. Much of the occupants of that building were lost in building 1 WTC or WTC 1, and in 2 WTC, the North Tower and the South Tower. You'll see me use those words interchangeably. The 3rd building we studied was up here. It's called 7 World Trade Center or World Trade Center 7. That was a building that was only 47 stories tall. The plane did not hit it. However, the building collapsed at 5:20 that afternoon. So as we know, most of us know, at 8:46 is when the first plane hit the North Tower. I'll show you that picture. And at 9:02, you had the second plane hit the South Tower. We had 4 objectives: determine why and how these 3 buildings collapsed following the initial impact of the aircraft, in the case of the towers, and why and how did the 47-story WTC 7 collapse. The second component of this was determine how the injuries and fatalities were affected by the evacuation, the fire response, and the occupant behavior to that event. The third was to determine what procedures and practices were used in the design, construction, and operation of these buildings over their life. The reason being, there were some people who thought that the buildings may have some issues. And the question was there anything in the buildings themselves that may have been of concern? And finally, of course, at NIST, most of what we do is to help improve for the future. Therefore, what other areas in current building and fire codes that would warrant revision, including standards and practices? That's a very classic NIST mission area, and that's what we focused on. And you'll see here, this picture sort of captures, here's the North Tower. The airplane came in on the north side of the North Tower at 8:46. It collapsed after 102 minutes, roughly at about 10:30. The second tower, the South Tower, the plane came in from the south and slightly lower in height. Came in at 9:03, actually, close to 9:03, 9:02, 9:03, and collapsed in 56 minutes. So it had collapsed before 10 o'clock. Of course, this asked the first question: why did the second building, which was hit 16 minutes later, collapse first? That's a very simple question that comes to mind. And for those of you who might be familiar, the planes were almost identical. There were 767 Boeing planes, 2 commercial airliners, with people and jet fuel and luggage. And so we had to account for those factors as well. Part of that 9 or 8, 10 or 11 months between 9/11 and us launching the investigation was us briefing the Hill in terms of what authorities we need or to be able to do this, and to convince the Hill that NIST was the right organization to do this. This isn't, even though over history, as Willie will say, we've done investigations going back to the Baltimore fire of 1904. What we did not have is a comprehensive set of authorities to deal with something as complex as this. So Jack Snell, who was the lab director at the time, Willie probably knows him quite well, and myself, we briefed the Hill multiple times. We briefed the Department of Commerce, and ultimately we got this authority. And the director of NIST at the time appointed the National Construction Safety Team for this particular investigation. And that was 14 people listed on this, listed here, who I think all had a very important role to play in carrying out this investigation. They were the core team that drove much of the work. We had a total of over 200 people who participated. So this was 70 additional NIST people, 14 core teams, so that's 84, 85, and 115 external experts and contractors. This was not some bunch of yahoos sitting in one corner doing its own thing. This was a very large team of people across industry, academia, and NIST. The other thing we did in this investigation, which NIST classically does not do, is it was open process and transparent process throughout the investigation. We held 23 public meetings and briefings, including 7 in New York City. We actually, our plan, the draft plan for the investigation was shared in New York City at a public meeting in June of 2002. And we had people testify at this public meeting about what should be included or not included, what they have inputs for us, and what the concerns were. So the families of victims, they were the strongest advocates for this, but also industry was very much involved because they felt the buildings were not at fault. Buildings are not designed for aircraft impact. Keep the terrorists away from airplanes and airplanes away from buildings, and everything would be fine. So there's no need to do anything about the buildings. And of course, the truth is somewhere in between. And so our job was to navigate the two different stakeholders and perspectives, and to make sure we were objective and impartial as we carried out our work. And so we had lots of scrutiny throughout the process. We also put out updates for the media and for the public. We did any reports that we published, including the final reports, we put out in draft form for public comment for at least 60 days or 90 days before we then got all of those inputs, refined the report before they're final. We had an external advisory committee that looked at what we did and before we finalized the reports as well. And we had a website. So things that we normally at NIST would not have done historically. All right, so that's just giving you a little bit of a sense of the setup for how we went about doing this. Now, let's talk about the buildings themselves. These were very innovative building designs. 110 stories at that time was the world's tallest building. In fact, if I'm not mistaken, even on 9/11, they were still the world's tallest building. And how did they get there? There's a lot of money spent in developing buildings like this. The real estate development world puts a lot of money into this. It's an investment. What are they trying to get out of this? A return on investment, right? So what they want is, if they're putting a building together, they want to have leasable space. They want to maximize leasable space. So by having a 110-story building, you want to have on every floor lots of space to lease, and the minimum amount of space used for the utilities and elevators and stairwells. Right. So you needed that. So what did they do? One, this planned area of the building, each building is an acre, 208 feet. Think about this as an acre lot, flat acre lot. Okay, not a 1/3 acre, not 10,000 square feet, it's an acre. And you want to have, what they did here is mask all the columns. In a typical building, you have lots of columns all over the place. All the columns are put out on the outside of the building. So, and as a tube. And the remaining columns were inside the core of the building. So you had open floor plans that people could adjust. There are people who lease the space can adjust however they want to adjust it and break it up or keep it open. In order to do that and have the smallest central core, they came up with another idea, is to think about this 110-story building like a Lego-like structure. So you can think about this as 3 high-rise buildings stacked one on top of the other. Because if it was a normal high-rise building, you would have had to have elevators go to every floor, from floor 1 to floor 110. And maybe some would, stop at different places. By doing this, what they had is a sky lobby at 2 levels, express elevators that took you to those sky lobbies, and then you took local elevators. So these local elevators for these three stacks use the same central core space, right? So you minimize the footprint of what you had to use, with the result that this side was 60 feet long as a single open span and 35 feet on the other side. And you'll find that this is one of the longest spans for the floors in many buildings. Another innovation of that time is, I use the word Lego-like construction. It's Lego-like construction. Normally, if you've looked at a building, the columns are very big at the bottom. As you go higher and higher, the column sizes become smaller and smaller because it's less and less weight on the columns. In this particular case, you will see they had 14-inch square columns, and all the columns surrounding on the outside were 14 inches square, top to bottom. How do they do that? They did that by changing the thickness of the steel that you see here. Outside is 14-inch square, the thickness of the steel has changed, and the grade of steel has changed, the strength of steel has changed. They had 14 different grades of steel that they used here. And every panel that you see here, three columns by 3 spandrels, 3 floors tall, had a number stenciled on it. And there was only one location where this particular panel would fit in the building. Not done typically in most construction, if you go and look at that stuff. So, and And that's how these things got put together ultimately. And then the floors, and here you see the 60-foot long truss. Normally you would have a floor with a beam and girders and concrete and things. This was a truss, a lightweight truss. And we won't get into all the details here, but I'll simply say very unusual to do this. Minimize the weight. You're minimizing the weight of the building by making sure it's adequately stiff and strong to carry the weight. Okay. So there's the innovation in the design. Our role was to figure out how these things collapsed, given the fact we had some physical evidence. We had lots of visual evidence. We had lots of documents, but our primary way of analyzing the collapse was reconstructing using models, physics-based models. Think about it. And the sequence of collapse involved at least 4 different things. First, you had the airplane hitting the buildings. And whatever that interaction did, the damage that it caused is one step, the airplane impact analysis. It's step 1. That means you have to model the airplane, you have to model the building, and you have to model the momentum with which the airplane hit the building and the damage it did to the building and estimate the damage. The second thing that happened as a result of the airplane impact is that jet fuel was spread into the building, which ignited fires. And the fires then developed and spread. So you had to model the fire spread. That's a totally different analysis. I know there's some engineers in this group, maybe not everybody is an engineer. But airplane impact analysis is one kind of expert analysis technique. Fire dynamics is using computational fluid dynamics, totally different analysis tools. The third thing, when you have fire moving around, is you can predict the gas temperature, which would be the temperature of the air in the space. You would then have to figure out how hot the steel got. It's called thermal analysis, right? So the fire moves around and then the steel, which is at, let's say, room temperature or whatever temperature was there that morning, starts to heat up as the fire comes around slowly. And so how hot does the steel get? And what happens to the properties of the steel as you heat it up? That's the thermal analysis. Well, all this is going on. What's happening to the structural capacity of the building? The airplane impact damaged some of the structural elements. The heating of the steel is weakening the steel. The combination of the damage from the airplane plus the weakening associated with the steel is what is included in the structural response analysis. So all of that had to be modeled, and that's 4 separate analysis techniques, each of which is a pretty hairy set of calculations. I'm using the word calculation, which is really not the way you do it with a calculator. These are very complex simulations, right? So, and then you have to hand off the results of one analysis to the other. Some people might use the word interoperability. Well, the state of the art is not, even today, is not one that allows for that type of interoperability. It has to be hard-coded from one to the other. So what you see here is the simulation of the airplane impact. The first simulation is showing you World Trade Center 1, and the second simulation is showing you World Trade Center 2. So let me, just trust me, these are very exquisite detailed analysis. You can see the debris. You can see, if you hadn't seen it before, let me repeat this once more. And you'll see how the airplane disintegrates as it goes through the steel. And you can also see what happens to the structure and the fireproofing on top of the steel, and so forth. Look at again what happens to the second airplane, how that disintegrates. And we had maps of all the elements that were damaged. The one thing I do want to say is the following, right? So the airplane came in from here, the north, for the North Tower, exited from the south. In the case of the South Tower, you're seeing a plan view. This is an elevation view. The airplane came in from the south at an angle and exited at the northeast corner of that building. So let's look at what happens on the south face of this building, right? So the North Tower. This picture is of the south face. And it's just about 6 minutes before the building collapsed. And you can't really see this really well, I don't think. But if you were able to see it well, let's see if I can find the cursor. Okay, here we go. This is supposed to show you 55 inches. What has happened is the column that was here has moved inwards and bowed 55 inches. 55 inches is 4.5 feet. So that has happened because of the heating at the back. It's not where the plane came in. As you can see, the plane came in up in the front. A lot of the damage is up in the front. There was only one column that was damaged at the back, but this area is where you see all the inward bowing happening. Likewise, in the second tower, you see the inward bowing happening on the east face, and it's roughly 10 inches, 18 minutes after the impact. And obviously before it collapsed, it was much more. So what the airplane did is it caused a lot of damage to the structure, to the fireproofing that covered the steel, and allowed a lot of the, it opened up a lot of places for oxygen to go in to help fuel the fire, in addition to the combustibles that were there. And it turned off the water supply system, so the sprinklers would not work. And it damaged and dislodged the fireproofing and allowed heat to be transported quite easily. So as you can see, if it had just been airplane impact and no fire, those buildings would still be standing. Okay, that's the main lesson. The second piece is it's the airplane impact plus the fire that led to the collapse. So we had access to a lot of visual data. We collected in excess of 7,000. We actually analyzed in excess of 7,000 photographs taken by more than 185 photographers. We analyzed more than 150 hours of videotape from the major media news outlets and more than 20 individuals. The number of photographs we actually ended up collecting later on and made public was more like 90,000. It's on our website. But these were the key ones that we analyzed in great detail. What we were able to do with this visual analysis is identify the significant events for the two buildings, to the aircraft impact, the fire development, and the building damage. What was the orientation of the airplane? what was the initial damage to the face of the north face of building 1, the north tower. All of that you could do with exquisite analysis. And you could also develop detailed maps of the fire, smoke, and the condition of windows. Window breakage means oxygen can get in. We could do all of that. And so here's the next step of the analysis, which is the fire dynamics. I just want you to know that the airplane came in from the north. This is again the north tower. Fire started, and you'll see by the time this is done, the fire's at the back end. So what you'll see, and I'm not going to wait till the whole thing gets done, you'll see that the fire is the back end. This is where we have the inward going. I showed you the 55 inches. What I'm also going to show you is we did laboratory at NIST, the large fire laboratory. We did recreations of the workstation modules in the building with actual workstations from the World Trade Center tower with the configuration that is there to validate our models before we predicted the entire building. The pieces of steel we got, how do I know there were 14 grades of steel? In addition to the documents we had, we actually did high-speed impact tests to also determine the impact properties of the steel. This is called the Kolsky bar apparatus at NIST, where we actually did those tests. So it wasn't that we were just picking up stuff from elsewhere and assuming things. We actually developed a property database to put into the models. We actually got how was the workstation actually located in the fire dynamics model, so we could actually model the combustibles in the building to a lot of accuracy. All right, now I'm going to show you the end of all of this, okay? And which would be, just watch this, the first, the left building, which is the Tower 1. Plane came in from here. I told you, watch this antenna. And I said that the inward going happened on the south face. You will see this antenna will tilt to the south, and you'll see that it actually the building tilting to the south as it collapses. Okay. And now, and this is World Trade Center 2. Plane came in from here, exited on the northeast corner. This is where I showed you the inward going. See how the building tilts towards the inward going as it collapses. So I'm going to let this first one go. Watch the tower, it's going south. And I've turned off the audio for obvious reasons. Now let me turn the next one on, and you'll see this one tilting to the east. Consistent with the models which show the photographs which show the inward going on these faces. So I think it was very easy. I mean, it took us 2.5 years. We started this in August of 2002. We issued our draft report in June of 2005. It took us 3 years to do all of it. Collect all the information, analyze, build a model, analyze the information.
Shyam, 3 years and how much money, roughly?
Nominally, we asked for $16 million from Congress. The Congress, I forgot to mention that. We got that through a special appropriations, and that money actually got transferred to us in September of 2002. And I will say there was a lot of research money also that was augmenting the investigation money, because the two are feeding off of each other. So, but nominally 16. In terms of time put in, I think there's countless hours. Let me just say that the 200 people who worked on it, particularly, I'm going to say nearly all 200. And by the way, that also includes people, not just the technical experts, but also there were people who were from public affairs, chief of staff, the congressional affairs. This was the full court press on the part of this leadership, because you needed all pieces of acquisitions, human subjects, you name it, all those issues were involved in this. So we had to have everybody engaged as a single team with a very single goal. But I will say that there were, for at least the first 3 years, it was almost continuous. It's a love of labor, almost continuous work. There was nothing else we did, pretty much. There were a few other things we did, but this was a big deal. Now, in addition to the collapse analysis, we also spent a little bit of time interviewing occupants, not a separate whole project, the surviving occupants, and also emergency responders. These were exquisitely done using, for surviving occupants, we had telephone surveys for 800 of them, and then face-to-face, 2 to 3 hour long interviews, structured interviews with them as well. Emergency responders, all 116 were face-to-face interviews, 2 to 3 hours each. This included a large number from the Fire Department of New York, Police Department of New York, Port Authority Police Department, and security personnel, building personnel in the buildings. And I sat in on some of them, and just so that you know, the 9/11 Commission, their interviews that they reported in their report were the same interviews that we had arranged with the City of New York to do, the Law Department of New York. So we collaborated with them, allowing them to join us in these interviews. So I think the most important pieces of information to take away from these interviews are, there were roughly 8,500 to 9,000 occupants in each of the buildings that day. Typically, there have been 20,000 people at full occupancy. So the reason being, this was, it was the first day after Labor Day. School had just started. It was early in the morning. People hadn't yet gotten to work. It was primary election day in New York City. It was a Tuesday. So all of those factors mitigated the number of people who would be in the building at that time. What is important is 87% of the occupants of the tower were able to evacuate successfully, which you don't know. You wouldn't know that, but because the number of people who died is so large. And 99% of those below the floors of impact were able to evacuate. So
Shyam, you're saying some of the people who were actually in the building above the point of impact also got out safely?
Of very few. Most of them were below. So yes, the difference between 99 and 87 comes primarily from building 2, the South Tower, because when the first tower was hit at 8:46, people knew something was wrong in the other building, and they all took the elevators and got out in the second building. So 3,000 people self-evacuated World Trade Center 2 using the elevators and stairwells during those 16 minutes. That's why that's why you see this mixed numbers in terms of success rates. But once the second building was hit, the number of people above the impact floors was very small. That number was small once the building is hit, because the stairwells are knocked out. Now, the other really important takeaway from this was that about 6% of the occupants, surviving occupants, that would be 1,000 people, they reported a pre-existing limitation to their mobility. Now, when we think normally about mobility impairment, we think in terms of people who might need a wheelchair. That is probably not, that is not even the full story. And what we found was people who might be on blood pressure medicine. There might be people who are pregnant. There might be people who are obese. There's any number of reasons why there's mobility impairment that would prevent them from climbing down the number of stairs that they had to come down. Think about this. How many of you have climbed down 10 flights of stairs? I know Willie has definitely done that. How many of you have climbed down 20 flights of stairs? Okay, there we go. Now, as you start doing this, start doing 30, 40, 50, 60, 70, and then you start seeing the problem, right? So maybe the person who does the marathons would be fine with coming down 110 flight of stairs, but a lot of us probably won't. So I think this is, and buildings aren't designed for full building evacuation. They're designed to evacuate one floor, the fire affected floor, to the adjacent floor. So at any rate, if there were 20,000 people in each of those towers, the evacuation would have required 3 hours. The buildings would have collapsed, and the death likely would have been 14,000, not 2,750. So that's just a point of reference. And a final piece on this is that we found challenging radio frequency communications, which has led to a whole bunch of research in public safety communications, but also the protocols for very large scale operations does not exist. There's so many different emergency responders, so many different channels in which they're communicating. There's very little unified command and control and protocols, and even in training to do that sort of stuff. Given the time, I'm going to take it a little bit quicker on building 7. I suspect there will be more questions on building 7 for various reasons that I'm used to getting those questions. What I want you to look, this is building 7, the floor plan. This is the south face of the building. This is the face that faces the north tower. This is the north tower of the building. What I want you to focus on is column 79 and this general area. Whoops. You will see, much like the towers, you have very large floor spans. And you'll see these, you see column 79 here, column 44 here, and column 80. There's no column between 44 and 79, 79 and 80, 80 and 81, and 81 and 26. However, between 35 and 40, there are 5 here. There's 2 more. So there's 7 here. There's only 1 here, right? So what I want you to think about is the exterior has a lot of columns, keeping it relatively stiff. You have 79, you have all these horizontal girders pointing into this girder here between 44 and 79. And then you can see there's no symmetry on the other side. So if there were a girder here pushing back on these other girders, you would see some kind of a balance. Here you don't. So there's no support on this on this side here that my arrow is showing. So just keep that in mind. So I'm showing you the same thing here. This is where the exterior wall was. This is column 79. That is 80. That is 81. And that's the other 20 something. You can see here what this attachment looks like. You have these horizontal girders. There's nothing here pushing on the other side of these horizontal girders. This girder, this particular girder is sitting on the seat It has two bolts, and that's pretty much it. It's not unusual, it's okay. But what causes this building to collapse is the following. As this this floor gets heated up, what happens is the exterior is very stiff. The floor is being heated up, the steel expands, the thermal expansion of steel is more than that of concrete. So the steel expands, and of course, what's connecting it to the concrete starts to crack. And as it expands, those girders that we saw before, pushing on this particular girder, this is column 79, this is column 44, pushing it hard, and eventually that gives way, and the support for that column 79 goes away. So that, just remember that. And what happens actually is, when you do the actual simulation, which we have done, you find that on floor 13, it breaks away, and then
that better? Okay, that seems to have done it.
okay.
Sorry.
Hopefully you can hear me now. And you can see the screen. Okay. So I hope you heard what I said, which is that because of the thermal expansion and the breakage of that floor on floor 13, that floor fell on floor 12, which then fell on floor 11, and then it keeps going down, and until you have this column 79 unsupported between column 14 and column, I'm sorry, floor 14 and floor 5. So you have 9 stories where this column is unsupported. It buckles as it would, just, it has no support, it just buckles. And that then leads to vertical propagation of failure to the top of the building, to the east penthouse, which I'll show you later. And you'll see that what happens then is column 80 fails, column 81 fails, which are just, on the same line with column 79. And once that happens vertically all across the east side of the building, then it starts to move from east to west because you're losing support. The floor is starting to fail, and it goes from east to west. And so,
Shyam, the
Good.
audience perhaps doesn't know, we had a number of these beams on our campus for what, 5 to 7 years. Were there any tests that were performed to verify the theory that you just projected? Or did all that information come from the simulations?
So in the case of building 7, there were no pieces of steel
So
found.
ours were just from the two main towers.
Correct. The 236 pieces of steel were from the main towers, and you could identify them. Now, in the case of WTC 7, we were not able to identify on site or to bring and identify at NIST steel that was from that building, because this was a generic building. Unlike the towers, which were, as you know, stenciled and exquisitely designed, we were not able to do that. But there were a number of other World Trade Center buildings that also collapsed that day, as you know. It's not just one. There were buildings 3, 4, 5, 6. The hotel also, was damaged. So those were more generic components. So no. So this is, now you'll see where the validation is going to come. How did we validate what we saw? And the thing you have to now look at is, look at the evidence, which is, this is a picture actually from a video, and I'll play the video. This is the East Penthouse. I mentioned to you that East Penthouse has a kink. Here's a picture of the kink. Right, if you draw a right line right below that is column 79. Okay, so East Penthouse has kinks. There are window cracks all along the same line of column 79. So it wasn't, we didn't start with looking at the observation and figure out what to do. We did our analysis and then we figured out, okay, what evidence do we have to prove that this is actually happening? And look for the videos and pictures to see it. So this is what you will see. And to give you what it looks like at the roof of the building, this is the East Penthouse. This is how column 79, 80, and 81 looks. The kink is this red line that we see. And you can see this kink here. The other piece you see is the fulcrum for the kink is the end of that East Penthouse. This is the west, the other penthouse, I guess the west penthouse. But the more important thing is the kink is directly below column 79, or column 79 is directly below the kink. Now, watch this simulation. This is going to be an interesting simulation. There's a clock here, which will work. This is the simulation. This is the video. And this is a picture of vibration, horizontal displacement that we saw going as the building. You can start to see the kink forming here, as well as here, and the failure start at the bottom of the building. I'll replay it. I know this is very difficult to see 3 places at the same time. So watch the bottom here for failures. That's the column 79 failing here. Then you can watch the kink here and here develop, and eventually they'll start to collapse. A couple of words on this. The model that was used for this particular piece of the analysis was called LS-DYNA. Some of you may know that term. Computer tool. It was so detailed, the amount of time it took to make one run was 6 months. one run. And it was using a bunch of clusters. This is again, 2007, 6, 7, 8. So these were multiple CPU clusters, not a supercomputer, but on the other hand, not just a desktop type thing that was run, and it took 6 months. And we did, of course, multiple runs to make sure, how to make sure it works correctly and what the level of uncertainty is in these analyses and so forth. The other comment to be made about this type of analysis is anybody who's done this will know that in analyzing structural collapse beyond, there are stability issues in numerical analysis. Anybody know about numerical analysis, stability issues? When you go beyond the normal continuum realm, Newtonian field, and when things start to break apart and you become unstable, numerically they become unstable as well, right? So to keep this analysis running when you have an unstable physics along with an unstable numerical analysis is very hard. So you can't really go all the way to final collapse where every piece is understood. You can only do it to a certain point in time. And so the fact that we were able to do this close, and this is the world I live in. I've lived in for all my career, pretty much. And I'll say this is the most sophisticated I have seen anyone do things of this caliber that actually makes sense. The other piece, the airplane impact analysis and the other analysis that I talked about would take 2 months for a run. That was simple compared to what we did here. And remember, airplane impact analysis is also not a simple, trivial thing. In the past, in the defense world, what they do is they take a jet fighter and then they figure out what happens if it goes into a nuclear power plant. Hypothetical, right? I'm just talking as an
Shyam, why were we so lucky? Why did we get this assignment? That's a rhetorical question, of course.
Why, I don't know really, other than the fact I pushed a lot for it. I will be honest with you, I pushed a lot. Jack Snell and I,
But why did we want it?
Let me put it this way. NIST has done these investigations in the past. We have a long history of doing it. We are very proud of having done these things.
Trying to say that wasn't our first rodeo.
It wasn't our first rodeo.
A building and fire research laboratory that.
The Kansas City Hyatt Regency walkway collapse. If you look at a number of high-profile events in the past, the Mara building collapse, the earthquake, San Fernando earthquake, post-disaster investigation. Number of these things. We have a long history of doing this, and we felt that this was something. I think we bit off more than we thought we were biting into at the time, but also probably naive idealism on the one hand, I think, played a part in it, and also the just sheer horrendousness of this entire incident, and the fact we wanted to learn for the future, and we wanted to make our contribution to the nation in some fashion, and this is the best way we thought we could do it. So I think that would capture, So we completed our investigation. We issued reports just to complete this story. 43 reports on the towers, 10,000 pages long. You can find them all published, available online. 3 reports on WTC, 7,000 pages long, both of which have summary reports, roughly 250 pages for the towers and 130 for 7. We made 31 recommendations. Major US building fire codes have adopted those recommendations, which I'll consider comprehensive and far-reaching, and all within 5 years of our study. Now, have you ever seen national building codes change in 5 years? I haven't since then either. So we were able to accomplish that because of just the importance of the event and the public engagement on it. I can get into the specifics of the changes, but everything from better fireproofing to better fire resistance rating and structural integrity to better ways to evacuate occupants and have fire service access to buildings and emergency responder communications, all of that. And of course, our recommendations have had a significant impact on design and construction practice worldwide. So when you look at all the new buildings that have come since then, including the Freedom Tower, the new Building 7, which was built, as well as some of the very high-rise buildings in the Middle East, in London, the Shard, and in China, and Taiwan, and Malaysia. There are pieces of our recommendations that have all been included in those buildings. And 3 very quick things before I conclude. We were, as a result of our investigation, built a national fire research lab. This happened, we began construction in 2009. What you see is our existing lab, which is there along with the exhaust system. This is the new lab and the new exhaust system where we can actually test structures under fire that are being loaded. That means structures which are undergoing, loads or forces that you could impose on them while there's also fire, which is a unique capability in the entire world. That doesn't exist. This is because of 9/11. So we can get to performance-based design. We have established a world-class resilience program. Resilience is now the word, by the way, just so that you know, we started the resilience program at NIST in 2007. Everybody uses the word resilience today, but that's when we started. We are now the lead agency for the National Earthquake Program, multi-agency, $130 million a year program. We're the lead agency for the National Windstorm Impact Reduction Program that deals with hurricanes and tornadoes and storm surge and so forth. And we have expanded our research on fires in the wildland urban interface, which is so important, particularly on the West, but also in the East. And we have established a disaster and failure studies program formally. And this gives you what Willie was driving at, all the various investigations we have done, at least since the 70s or 80s. And most recently, a year ago, many of you probably followed the Champlain Tower South collapse in Miami-Dade County in Florida. We are investigating that failure at this point at NIST, not me. Folks in the engineering lab, and that is probably quite as complex as what we did for the World Trade Center, because in that case there was no airplane, no hurricane, and nothing that was untoward that caused that building to collapse. And so it's going to be very interesting to find out how and why that building collapsed and what changes are going to come out of that. So with that, thank you for your attention. I'm sorry I took a few more minutes longer than.
So for questions and answers, we might start with folks here and afterwards look at some of the questions in the chat. Yes.
We're going to be very quick. I know we have students that are Muslim. They want to go and pray. And I have 1 or 2 that are also supposed to be at home by now. So the first one from my layman angle is on referencing your slide 23, I believe, either 23 or 24, where you made you said something about global collapse. Either 23 or 24, 22, but you did mention, okay, right there, beginning of global collapse. And as I read that, I was thinking of Chinese inroad. I'm looking at the space beyond the United States now, given the position of the United States in global politics. And I'm looking at Africa. I'm also looking at Chinese inroad, all in the so-called quote unquote infrastructural development. And then the question is there any effort to mitigate or eliminate Chinese inroad in Africa in terms of the so-called? That is one. Two, I'm fascinated by slide number 12. And 3 of our students here are doctoral students in information systems. And I think they will be interested if you could shed more light on this particular, the last bullet, talking about the complexity of the operation. Was there a breakdown of communication, information systems during the period, and what has been done since post, as a first responder in a post horrible event that occurred on 9/11. And I think I will pause. No, let me put the third one. Steel or concrete is a general question. I'm trying to frame a question for either an undergrad or graduate students giving a lecture of this type, and I'll say steel or concrete. What will you choose? Because from your presentation, I'm thinking, wow, perhaps without the horrible event of flying those planes into the south, the two towers, given the structural analysis and the absence of, physical, how do I put it now? And perhaps the building collapse, maybe years to come. I may be wrong. I'm not a physicist or civil engineering or whatever. I'm a historian. So I'm just asking those questions within the context of a layman. Thank you. But brilliant analysis, easy to follow, unambiguous, and I think you deserve another clap.
I'll stay out of politics a little bit. I'll give my personal opinion at this point, but
We can look into that.
On the issue of protocols and communications that are for the emergency responders. First of all, I think one of the things that hampered folks on 9/11 was the Emergency Operations Center for the City of New York was in Building 7. So the power got knocked out. The building ultimately was fully evacuated. Nobody died in that building. It collapsed at 5:20. So given that fact, there was no emergency operations center in that. The designed emergency operations center was not working. So they had to then come up with an alternative to do that. So that's one thing. The second is, the scale where you have 400 emergency responders. And without the glue, the normal organized staging and communication and coordination and command and control, you had people volunteering and showing up at the site. And they were on their own little group radio channels. So that's one component. So in terms of the protocol of hierarchy between, the various units going up to command and control was not as streamlined and as functional as should be the case. Now, adding to that was that the type of radios that people were carrying were not such that worked very well within the buildings. I think this is a well-known problem, at least that is how do you work in steel and concrete buildings where radio frequency transmission is not very good. And so I think better repeaters within the building and other kinds of in tall buildings are really important to be able to enhance that communication within the building of the emergency responders being deployed into such sites. And I think there's been a lot of work done in improving the technology, the public safety communications technology per se. And there's also a national level command and control system that's been put in place. It's all well documented. I just hope, since I haven't followed exactly the training that goes on at the local level, I just hope if there's ever 300, 400 people or 250 people show up, there are protocols that people have trained for this. You have to have trained for this to be able to do this really well. That kind of different groups doing their own thing. So that part I don't know. So it's where as I said, the rubber meets the road. It's where the implement. You may have everything on paper to look beautiful, and you can do tabletop exercises for all you care, forever and ever. But ultimately, it's going to be how it operates at the local level. And I think the technology part is easy. There are public safety communication systems that are being developed. I think the operational components at the local level, I hope, is being given attention by not just New York City, because this can happen in many other places in the country as well. So that's I think that's one answer to that, at least one perspective. On the question of steel versus concrete, I think the most important thing we took away from all of this is we're not calling for buildings to be designed for airplane impact, right? So all the building code changes are about what's appropriate, as I said here in slide 24, things like improving fireproofing so that when something hits a building really hard, it doesn't get dislodged. The bond strength is far better. The installation is much better. The inspection is better, so the quality control is better, so that it has more ability to stay, not for an airplane impact, but for other events, particularly for high-rise buildings. And we actually make a distinction between buildings that are either 120 feet and more or 400 feet, 420 feet and more. That's where the codes are doing. Because the consequence, risk is the input and the consequence, the hazard and the consequence. The risk is much higher when the consequence, because the consequence of a high-rise building is much more, because you have all the problems of evacuation just get multiplied hugely, and therefore the risk is much more. So it's risk appropriate type of approach to the codes, and a lot of these requirements are more stringent for high-rise buildings. So I would say so the way you would make the distinction between steel and concrete would be the same way you make it today, which is economics, technical ability to do the work functions you want it to do adequately and safely. So I think that those factors still are vitally important. And of course, there are improvements in concrete technology and improvements in steel, technology as well. A little less on steel, but more concrete.
Okay, John and Shyam, let's take a few questions from the Zoom audience.
My first question is in reference to slide 5. Was the figure on the left the top view of the building?
The figure on the left is the plan view or the top view of any given floor in the building, correct?
Second question, do you take consideration about the total weight of the planes while the building collapsed? And what is the weight limit for the planes?
So very, very good question. Momentum, as you know, is the primary driver of the impact analysis. And in the case of the planes, the simulation that we showed here, we had to make sure the massing of the plane was adequately taken into account. So in fact, the jet engines, they're very heavy, were exquisitely modeled. And the fuselage is not so strong, it's just going to disintegrate. We included how much jet fuel was there in which fuel tanks, which we got from American Airlines and United Airlines. Those were the two planes that were affected. We also got from the airlines the luggage trunk, the luggage cargo hold. And it turns out in one of them, there was seafood. And in the other one, there was some other cargo. So we actually had the explicit weight of the cargo that was in the cargo holds of the airplanes. And they were placed in the places that were appropriate. We also had to account for the human beings in the seats in the plane. So if you look at the detailed model of the plane, you'll see all of that in the plane. And I'm sorry I have to talk about the human beings as well, but yes, all of this involved people. And somebody once asked a question as to how did you guys work on this, given the fact that there was, all these lives that were lost. And the only way we could think about answering that question was the way I answered it a few minutes ago when Willie asked me a question, but also more importantly, how doctors do the work they do, which is clinically you do it. Doesn't mean you have no emotions. It's just that you do it clinically, professionally, and then you deal with it at your own time. But yes, I think these are the models for the planes were exquisitely detailed, as was the model for the structures.
Next question. Is it known whether or not the terrorists designed their attacks knowing that the way they did it, that it would collapse the towers?
Blind luck, or was it that by design?
Answer is no. I will say one thing, that is that the bad guys have all the technical expertise the good guys have. Just keep that in your mind as time goes on, that knowledge and expertise is not limited only to the good guys. So that I'll just keep that at the back of your mind, which is the basis of that question. So I completely respect that question. But on the other hand, even the building was supposedly designed to resist the largest airplane at the time, which was a 707, Boeing 707. In fact, we looked at a 3-page analysis of what they had done at the time, and it was just about the airplane hitting and some local damage that would be caused, but there was no consideration of fire. And therefore they said this building will not collapse under an airplane impact, but that was just the impact. So this was in the 60s. So nobody had ever done this combination of impact and fire. And as I said before, if it was just the airplane impacting the buildings would not have collapsed. And there's no way these people knew that the type of fire that would be generated, and how the fireproofing would be dislodged, and all of the things that would have had to happen to go from the initial airplane impact to the collapse.
But Shyam,
They would have wished it. They would have wished it to happen, but that's not what they
I'm
designed.
gonna give a non-professional answer. It was going to cause terror no matter what. In fact, if you fly planes into a building, independent of what's it's nothing good is gonna happen. So if the buildings had not collapsed like it did, it still would have been an horrific event.
You're absolutely right. And just think about it. If they had been successful, well, we know that they got 3 places, they hit 3 places, and there's a 4th plane, we don't know where it was going to hit. Whether it was the Capitol or the White House, we don't know yet. I mean, you probably.
It was on a trajectory coming toward NIST.
But we know Pentagon was hit, and we know that people died in the Pentagon, much smaller numbers. And it was a renovated space in the Pentagon, and we were involved in some of the assessment of the Pentagon as well. And I went and visited that place. That was a more local damage, not as spectacular, if you wish, like the World Trade Center. So I think Willie is absolutely right. Is the fact that terrorists could actually go after the world's superpower and show we can hit all your major buildings with airplanes. As simple as that.
Next question, how much thermal energy was estimated in the jet fuel?
It's not so much in order for us to do our analysis, it wasn't so much the thermal energy that we needed. What we did estimate was that much of the jet fuel got burned within the first 10 minutes of impact. So it wasn't so much the energy that the fuel caused, it is so much as jet fuel was the cause of fire ignition in the building. What burned for the next hour or hour and a half, depending on the building, was building contents. Okay, so jet fuel was not burning for an hour and a half. It got finished in the first 10 minutes.
Last question is, did the planes have explosives?
The planes, to our knowledge, had no explosives at all.
We also have a few raised hands in the among the participants.
Take them.
Let's see. I might need to turn on my speakers to see if we can hear them.
While you are doing that, in terms of the new codes that have evolved from this, are these internationally adopted by now, do you know, or the efforts to make them?
So
We may have some hope based on what he was saying about the Chinese skyscrapers in the developing world.
So how this industry operates, let me just give you a little bit of a sense. So in the US, you have model building codes at the national level. It's the International Code Council or the National Fire Protection Association. So they have adopted the changes. State and local governments adopt them into regulations. That's when you call it a building code, state and local regulation. So in the case of New York City, actually adopted the latest version of the International Building Code. And likewise across the nation, the jurisdictions usually adopted at the state level, in every state. So that's within the US, right? So now what happens internationally is that the design firms that are world-class in designing high-rise buildings of the type that we're talking about are concentrated in the US. And there's one company in the UK. So you can think about Skidmore, Owens and Merrill, you can think about HOK, you can think about a number of companies in the US where you have architects and engineers. And so when you see buildings generally being built, high-rise buildings, again, I'm talking about high-rise buildings. In China, like the World Financial Center in Shanghai, or in Pudong City, a lot of the buildings in the Pudong skyline in Shanghai, or in Beijing, or in Hong Kong,
I understand the Twin Towers in KL.
and in Kuala Lumpur,
incorporated those
or
standards.
Burj Dubai, was designed by SOM. So the designers are US, the construction companies sometimes will be from Japan, from Korea, a number of Asian countries, oftentimes they're among the best. So with regard to the issue of other countries building or other, not the UK, let's say not the US, but some other countries building high-rise buildings using their own domestic standards without access to international practices. I really can't say much about them. Other than to say, and I do understand the importance of what you're talking about. Personally, I know of many issues in the developing world that I'm aware of quite well. And the use of loans as a way to kind of rope in countries and so on. So without getting into the specifics of a country and so on, I would say those are not the best ways to move forward. But on the other hand, it's not I don't think there's a policing role that the US has in that regard. We can't really do much.
I just think the wake-up call for us is the fact that in the developing economies, they're always looking towards the United States for the best practices. And I think as DRED begin to think beyond this lecture, I think we may come up with a workshop tailored towards some of the government agencies, just as we did for EFCC. They need to be tutored. They want to get the best practices that they can adopt. And by His grace, you get something from my office that we can look into.
Well, if you wanted to coordinate that, I'm not really sure that's a responsibility of DRED, but
Okay.
but
Yes,
but I will call upon my friends to
sure.
provide whatever, like Shyam, to provide whatever support you need.
Mhm. Yeah. Thank you so much.
Thank you.
I have to-
Few more questions. In the analysis of collapse of World Trade Center 7, why was the expansion of external beams not considered as contributing to the house cake?
No, they were all appropriately modeled using appropriate properties of those elements. So when I describe what actually happened, it is how they actually responded to the fire in the building. So don't assume that those were not modeled. They were modeled, but they were very stiff. And because they were stiff, they did not move. Stiffness was incorporated into the model of the outer columns, the outer face of the columns. Stuff that would expand would be the things that are easy to expand, which are not restrained. The outer column would restrain that entire face from moving. However, the inner girder from 44 to 79 was not restrained in the same way. So it actually expanded, it was pushed by the horizontal elements and therefore was able to break away from the column 79. So it was included in the analysis. What I told you is it didn't have any effect.
Can you explain why the second tower collapsed in 50 minutes and not 105 minutes?
I'm glad somebody raised that question because I posed that question up in the front.
Yeah, I thought you addressed that in the lecture.
Yeah, so it's very simple. If you think about the North Tower, which was hit first, the plane came in right smack in the center, went right through the middle of it, and then came back at the back. The second tower came in on one side, but it came at an angle, and it got out at the corner, the northeast corner. So the difference, the simplest way to think about this in your mind is in the case of the North Tower, everything was symmetric. At the end of the process, you still had 4 legs. Think about it that way. In the case of the South Tower, you had a 3-legged stool with one side less supported. So that's the easiest way to think about what happened. But ultimately, it was the modeling that demonstrated when this thing actually initiated collapse.
Shyam, this is not a fair question. You don't answer it if you don't feel comfortable. But and with a responsibility like this, were you ever concerned about your safety or anything of that nature?
Willie knows this quite well. So the answer is at some points, yes. Not when we were doing the investigation. There was no concern. The investigation per se had nothing to be concerned about, I think, other than the criticism, in terms of, not satisfying the 2 extremes, not the 2 sides, as I said, the two parties, as I said. Ultimately, we were able to go right in the middle and people were okay with it.
But there was never any pressure from the Hill, the politicians of the Congress for us to come out with any particular answer.
Zero. There was no political pressure of any sort, whether from the Department of Commerce, from the White House, or the Congress, or NIST management, to be honest. We were given complete autonomy as far as the technical work goes. And so as far as the technical part of all of this goes, there was none. I think the 2 pieces where concerns arose was there was a large and vocal group of people who we would think who believe in alternative theories of collapse, and they, of course, at points in time would actually come outside the NIST gate and protest, whether it's in Gaithersburg and in fact a couple of times also in Boulder, and there were, of course, I have voicemails that I used to get from at least one gentleman, if not more, that were threatening with abuses of various kinds. In fact, even maybe the last one I got was 6 months ago from the same gentleman
really?
who's been doing this since 2000 and when, I don't know, over 10 years. But then we've shared the information with the FBI through our security offices, and they have reached out to law enforcement locally and wherever this person lives. He's a known quantity. He doesn't supposedly do anything physical to anybody. So that's one example. The more interesting example, which I think where I brought in Willie into this, was the prosecutors for the Guantanamo Bay litigation of the 5 masterminds of the 9/11 attack. Came to NIST about 10 years ago, and they wanted to learn from our reports and so on, and we gave them all the factual information. And then they said they would put me on a list of the witnesses to testify. And of course, that raised a flag in my head. Yes, they only want me to testify as to what we found in our investigation. But again, I'm sitting here and testifying in front of the 5 major terrorists.
In Guantanamo.
And I have to go to Guantanamo in the special plane. They would take me and keep me there during this period. And so I brought it up to our, of course, I let Willie know, but I also brought it up to security people, OSY people, and so on. And they can't do anything because, if you're going to do, whatever. So the interesting thing is, here we are in 2022 and the litigation still hasn't started. So every few years, if you read the newspaper, you probably find what's been going on. It's one thing after the other, and every few years, the prosecutors will reach out to us and so forth. And then we talk to them, and we have told them most recently we'd be happy to serve as a consulting expert as opposed to a expert witness, which is a slightly different thing. But anyway, we'll see how all that transpires.
One more question. It is understood that on paper, calculations and adjustments were made and implemented, but how were these modifications in the new building tested for resilience?
So with for the new buildings, so our recommendations were actually very, pardon the pun, concrete. So they were not about doing calculations. It was about how wide a stairwell should be, or what should be the strength of the enclosures around stairwells, so they don't just poof collapse if something bangs into them. If that's the last line of defense of the people evacuating the building. Or if it's the fireproofing, what should be the bond strength, and so forth. So our recommendations are very specific and actionable, and how industry chose to implement it is for them to do so. That's why they are there. In fact, one of the recommendations we had was to increase the number of stairwells in a high-rise building from 2 to 3. It used to be 3. It then got reduced to 2. And we then said anything over 480 or 420 feet should be 3 stairwells, unless you design the elevators for occupant evacuation, which can also be done. We actually, ASME, the American Society of Mechanical Engineers, has adopted standards for both occupant evacuation elevators and for fire service access elevators. Those can be used in an emergency. So if you don't want to put a 3rd stairwell, you need to put a fire service access elevator in the building. So we gave them all of those options, so the industry now has choices to actually implement. So it's not about models that they have to use, they actually have to implement specific things.
Maybe one last quick question. So the World Trade Center 7 tower was ultimately damaged by fire that caused the thermal expansion. But how was it that the building caught fire?
So in the case of World Trade Center 7, remember that no airplane hit it. So what I probably glossed over, and I probably should show it, and I'll show it here. When in fact the North Tower collapsed at 10:30, which is and I want to go back again to make sure you're oriented correctly. So here is the North Tower. This building collapsed at 10:30. Here is World Trade Center 7. The debris from the collapse of this 110-story building hit the south face and the west face of WTC 7. And that's where that debris initiated the fire, okay? So what you see here, which I've stuck in here, this little picture, if I had to blow it up, is the south face of World Trade Center 7. What you see in red is damage to the exterior structural steel. What you see in yellow is the window glass is broken. What you see in green is no visible damage, and of course, blue, we could not see because of smoke or dust. And the gray stuff is vertically dark band, which we don't know what it is. Now, this here is the west face of that same building. You will see up at the bottom of this building, this red band, which is a damage to the exterior structural steel. And right next to it is window glass breakage and the damage to the granite and underlying truss right next to it. So, and this green stuff is no visible damage. So the lower floors, which is where we said we had the column 79 issue, 7 and 14, the lower floors were damaged, and that's where the fire ignited in that time frame in the morning. What happened was it took a long time for the fire to work its way around the building all the way to the opposite corner. Okay, so let's go back to the plan view of 7. What I just showed you is this face and this face, and the damage was here. Before the fire actually showed up here, that's the length of time it took to get to the northeast corner from the southwest corner. It took a very long time because it's a very large floor, and there was not a jet fuel, there were no breaking windows. There wasn't the propagation of fire at the speed that you saw in the towers. It was a much slower building fire. And this building had not so many open floor plans, so it was not easy for the fire to go from compartment to compartment to compartment to compartment, ultimately to the back of the building. So that's what took a lot of time to get there. All of that was modeled. It's in the report. So, I could have gone through all of that, but didn't want to bore you with even more information than I've already shared.
Should we wrap up? There is one last question. This last question has to do with sort of the microstructural analysis of the steel that was damaged by the fire. And if you could talk a little bit about some of the what at the microstructure level caused the failure.
I don't know what the question is trying to answer, but the properties of steel that are relevant to structural response and thermal response are not the microstructural properties, but the properties of the components. And all of these steels that were in this building, in building 7, if you're talking about building 7, were classical ASTM standards that met for those buildings. There's the ASTM E36, there's ASTM E50. There are a couple of particular grades of steel that are often used in structures. In the case of the towers, there were 14 different grades on the exterior, but on the interior were more conventional grades of steel. And so we know what the strength is, what the stiffness is, and those are the properties that go into the analysis as far as stiffness goes. We also have the thermal expansion properties that are well known for steel that we determined, and we use those. So we had the properties consistent with the grades of steel that were used. The microstructure of the steel was consistent with the grades that are part of the ASTM standards.
Thank you.
Well, Shyam, thank you for a very, very exciting and timely lecture. I think we had about 15 people or so here, but we had around 90 people on the Zoom tuned in. And according to Keyshawn, we still have about 50
Wow.
still tuned in now.
That's amazing. It's,
So-
you guys, you've been here till almost 7 o'clock. That's amazing.
You know, that's normal for me, but
All right, thank you so
so
much.
thank you
Appreciate it.
so much, John.